Hi, this is Alfosia Nihar from At Home Tuition. Welcome to our session today. The topic that we are going to discuss in our today's video is maxima and minima of a function. As the name suggests, this topic is devoted to the method of finding the maximum and the minimum values of a function in a given domain. It finds application in almost every field of work and in every subject. Let's find out more about the maxima and minima in this topic. Let me explain you some day-to-day applications. To an engineer, the maximum and minimum values of a function can be used to determine its boundaries in the real life. And to an economist, the maximum and minimum values of the total profit function can be used to get an idea of the limits the company must put on the salaries of the employees, so as to not to go on loss. To a doctor, the maximum and minimum values of the function describing the total thyroid level in the bloodstream can be used to determine. These are the few real-life examples. Now let us see the types of maxima and minima. The maxima or minima can also be called an extremum, that is, an extreme value of the function. Let us have a function y equal to f of x defined on a known domain of x based on the interval of x on which the function attains an extremum. The extremum can be termed as a local or a global extremum. Let's understand it better in the case of maxima. First, I am going to start with local maxima. A point is known as a local maxima of a function when there are maybe some other point in the domain of the function for which the value of the function is more than the value of the local maxima. But such a point does not exist in the vicinity or neighborhood of the local maxima. You can also understand it as a maximum value with respect to the points nearby it. If you look at this graph, you can understand it. Does this make sense to you? Okay, now let us discuss about global maxima. Please look at this graph. A point is known as a global maxima of a function when there is no other point in the domain of the function for which the value of the function is more than the value of the global maxima. See, did you notice that this is the highest one? There are a few types of global maxima. Global maxima may satisfy all the conditions of the local maxima. You can also understand it as the local maxima with the maximum value in this case. Alternately, the global maxima for an increasing function could be the endpoint in the domain, as it would obviously have the maximum value. So in this case, it is not a local maximum for the function. Similarly, the local and global minima can be defined. Okay, let me show you one graph to identify the different types of maxima and minima. Here is the global maxima and this is the global minima, and this is local maxima 1, local maxima 2, local maxima 3, and this one is local minima 1 and local minima 2. Hope you are clear with this graph? Okay, now let us move on to the next point, stationary points. A stationary point on a curve is defined as one at which the derivative vanishes. That is, let us consider a point x0 and y0. So consider this point as a stationary point of the function f of x if the derivative df over dx at the point x is equal to x0 is equal to 0. So this point will be considered as a stationary point if the derivative at that point is equal to 0. And there are few types of stationary points. Those are local maxima, local minima, and inflection points. We won't discuss inflection points in this video as of now, though you must note that all the points of extremum are stationary points. Okay, now let me show you the proof for that one. I'll prove this statement, the stationary point statement, for the case of a local maxima. Others will simply follow from this. Let's have a function y equal to f of x. Please notice that this function attains a local maximum at a point x is equal to x0. Near the extremum point, the curve will look something like this. The derivative is going to be positive here, 0 here, and negative here. Clearly, the derivative of the function has to go to 0 at the point of local maximum. Otherwise, it would never attain a maximum value with respect to its neighbors. This is all about the stationary points. All you have to know is, imagine there is a function at one point. The point has to be equal to 0 if you find the derivative. That is called stationary point. Okay, now let us move on to the next topic, the second derivative test. The second derivative test is the test is used to determine whether a stationary point is a local maxima or a local minima. Whether it is a global maxima or global minima can be determined by comparing its value with other local maxima or minima. Let's have a function y equal to f of x at a point x is equal to x0 as a stationary point. Then the test says if the second derivative d square f over dx square at the point x is equal to x naught is less than 0, then x is equal to x naught is a point of local maximum. If it is negative, then it is local maximum. Same way, if the second derivative where the point x is equal to x naught is greater than 0, then the same point x is equal to x naught is a point of local minima. If the second derivative at the point x is equal to x naught is equal to 0, then you have to check the following way. If for x greater than x naught, the first derivative at the point x is equal to x naught is less than 0, and for x is less than x naught, the first derivative at the point x is equal to x naught is greater than 0. That is, the function is increasing for x less than x naught and decreasing for the function x greater than x naught. We can conclude that x is equal to x naught is the point of local maxima. Similarly, if for x is greater than x naught, the first derivative will be greater than 0. For x is less than x naught, the first derivative is less than 0. That is, the function is decreasing for x less than x naught and increasing for x greater than x naught. We can conclude that x is equal to x naught is the point of local minima. Hope you're clear with this concept. So based on the second derivative test, you can describe the local maxima and local minima. Okay, now I'm going to show you the proof of the third case. The proof of the third case can be understood by the previous figure above for local maxima. Similarly, for local minima, one can get dy over dx is 0 at this point and negative and positive here. Does this make sense to you? Okay, now let me show you the proof of the second derivative test. We will prove the test for the case of local minima. The proof for a local maxima will follow in the similar fashion. One can see that the slope of the tangent drawn at any point on the curve, that is dt over dx, changes from negative value to 0 and 0 to a positive value near the point of local minima t. This means that the function that is represented by you can say that f of x, which is equal to dt over dx, behaves like an increasing function. Okay, the condition for a function to be increasing is df over dx is greater than 0, that is d square y over dx square is greater than 0. This confirms that the function will have a local minima if the first derivative is 0 and the second derivative is positive at that point. Hope you're clear with this concept now, second derivative test. Okay, now let me show you some solved examples on maxima and minima. Here is an example. We are supposed to find the local maxima and minima for this function y equal to x cube minus 3x plus 2. We will need to find the stationary points for this function, for which we need to calculate df over dx. Okay, we will proceed as follows. The first derivative of this function is going to be, if you apply the power at stationary points, dy over dx is going to be 0. So we will have, you have to set this equal to 0 and solve for x. Take the common factor outside, divide both the sides by 3 and set that and solve for x. X is equal to plus or minus 1. Now we have to determine whether any of these stationary points are extremum points. Here is where we will be using second derivative test. Let's now find the second derivative. Find the derivative of this again. That is going to be just 6x. For x is equal to 1, d square the second derivative is going to be 6, which is positive. Thus, the point 1 comma y of x is equal to 1 is a point of local minimum. If you check by plugging in the -1, you will get -6. So the point is the local maxima here. Okay, we can see from the graph to verify our calculations. Please have a glance over this graph. This concludes our discussion on this topic.